Let's take a look at Euclid's proposition 11 and proposition 12. This is constructing perpendiculars to a line, either from a point on the line or a point not on the line. Here's what the drawing looks like. Let's start with a line. Although it looks like a segment to us, Euclid wasn't all that particular about the difference between a line and a segment. Let's give these points some names. Let's call that one A. Let's call that one B. Okay, so we have this line AB. Let's add a point somewhere in the middle. Doesn't much matter where. Let's call that C. Okay, and we want to construct a perpendicular through C to AB. And here's how we're going to do that. We're going to pick some other point that's on AB. Let's call that one D. That's D. Okay. And let's draw a circle around C that has a radius of CD. So CD is a radius, and that gives us another point over here. Let's call that one E. So CD and CE are both radii of circle C. Now let's make an equilateral triangle standing on AB, and one of its sides is going to be DE. The center of the circle is going to be D, and the radius is going to be DE. There's a circle. And let's do another one centered on E, and the radius is ED. That gives us another point up here. What should we call that one? Well, let's just keep going through the alphabet. Let's call that one F. And let's connect F and C. And let's connect F and D. And let's connect F and E. So that's our drawing. And Euclid would have us believe that FC is perpendicular to line AB. How does this proof go? We were given that point C lies on line AB, and we constructed a circle with its center at point C, and we know that D is just as far away from C as E is. That's from our definition of a circle. We constructed an equilateral triangle using the methods you used in proposition number 1. Since DEF is an equilateral triangle, then DF must be equal in length to EF. FC, of course, is equal to itself. That's from the common notion number 4. We now have congruent triangles FCE and FCD. This is from side-side-side congruence, which Euclid described kind of clumsily in proposition number 8. And if Euclid had used the word congruence, it would have tightened up his descriptions a whole lot later on. Proposition 8 also gives us corresponding parts of congruent triangles are congruent, which is a very handy abbreviation, CPCTC, which Euclid does not seem to have used. And that is all we needed to show that FC is perpendicular to AB. For that, we're going to use definition number 10, which is kind of wordy. Definition number 10 says, when a straight line standing on a straight line, as FC does to AB, makes adjacent angles equal to another, as we saw that FCD and FCE are adjacent and congruent. Each of the angles is a right angle, and the straight line standing on the other is called a perpendicular to that on which it stands. So we've been able to construct this perpendicular FC through the point C, which is on line AB. So that's a straight line at right angles, which is to say a perpendicular from a point on the original line. But what if point C wasn't on the original line? That's proposition 12. Proposition 12. To draw a straight line perpendicular to a given line from a given point not on it. So let's start with a straight line. Let's make that line AB. and we were given an arbitrary point C that's not on AB. That can be our point C. You want to make sure that you don't draw this too large or it'll spill off the edge of your paper. Let's find some arbitrary point. That means it doesn't matter where it goes. Anywhere down here. That's our point D. And we're going to draw a circle around C that has a radius equal to CD. No reason to draw that radius. Now this circle, C, with a radius of D, intersects our line over here at a couple of points. One there. That can be our E. And it intersects over here. And let's make that one G. And we already know how to draw a bisector. So let's bisect EG. And we have a whole lot of points floating around here. And I'm not even going to bother giving those points names. Let's have a segment that goes from there to there. And I do want to name this point here. Let's call that H. That'll be H. And Euclid claims, and he ought to know, Euclid claims that CH is perpendicular to AB and goes through point C. Let's see what we've got. And let's complete some triangles here. Let's go CE and CG. And we've got a few things here that we don't really need, cluttering up our drawing. Okay, so we have our drawing. Let's do the proof. The first thing we have is a line AB and a point C that's not on AB. We have a point D that's on the other side of AB. It's farther away from point C, and we chose that. We drew a circle around point C with a radius equal to CD, a radius long enough to be sure that that's going to intersect line AB at 2 points, and we called those E and G. We bisected the segment EG using the method from Proposition 10, and we called the midpoint of that H. And once we had the points C, E, G, and H, we were able to construct some line segments. Postulate 1 says that you can do that. You can make a segment out of any 2 points. We find that HG is equal to HE because it's the midpoint. Those 2 segments are equal or congruent in modern terminology. CH is congruent to itself. Common notion 4 tells us that anything is congruent to itself. And CE is equal to CG. Those are both radii of a circle. So that comes from our definition of a circle. And then we can state that triangle CHE is congruent to triangle CHG, and that is from the side-side-side congruence in Proposition 8. Once you have 2 congruent triangles, then corresponding parts of congruent triangles are congruent. Specifically, angle CHE is congruent to angle CHG, corresponding parts. And that is enough to show that CH is perpendicular to AB using definition 10, our definition of perpendicular. So that's Proposition 12, drawing a line perpendicular to a given straight line from a given point not on it. So there we have Proposition 11, perpendicular to a line from a point that is on the line, and Proposition 12, perpendicular to a line from a point that's not on it. So you've seen the drawings and you've seen the proofs. If you like this video and you want to see more like it, there's my playlist, and you can subscribe to my channel and get notified when I put out new ones. Thank you very much.